A variation that we can consider on trees is that of a labeled tree. In this case, we still have a tree, so we're going to have a graph that has no cycles, a connected graph with no cycles, but now we identify each vertex with an element of the numbers 1 up to n. So for example, this is a labeled tree. If we want to try to enumerate all labeled trees, for example, on n equals 3, how could we do that? Well, we have, remember, the structure of a graph of a tree on 3 vertices looks like this. But now how could we label the vertices? Well, we could do it like this, okay? And that is actually the same tree as this. It doesn't matter if we flip the tree around, okay? What else could we do with another tree that we could do? Well, we could also do 1, 3, 2. That's a different tree. Again, we can flip the tree around and it's the same tree. It's the same as this one. What else could we do? Well, we could also do, what have we not done? Let's see. Starting with 1, I'm pretty sure we've done everything, but we haven't done 2, 1, 3. We haven't had 1 in the middle. This is the same as 3, 1, 2. And that's it. So there are 3 trees for this example. There are 3 labeled trees on 3 vertices. If we were to do another example, one that I ask you to do for homework, you will find that for n equal 4, there are actually 16 labeled trees. So you can think to yourself, well, 16. So that's an interesting count. We have 3 and then we have 16. Is there a pattern in the numbers that we see for the numbers of labeled trees? And in fact, there is, and we can count them. And it's a beautiful theorem that's called Cayley's theorem, which is an elegant result in graph theory. It states that the number of labeled trees on n is n to the n minus 2. So let's see how that works. If we look here at the examples that we had before, let's just check Cayley's theorem. If we take 3 to the 3 minus 2, that is indeed equal to 3, which was the number of labeled trees we found here. If we take 4 to the 4 minus 2, that's 4 squared, which is indeed 16. So Cayley's theorem is true based on the small data that we have. How would we come up with a proof of Cayley's theorem? Well, one of the most elegant proofs of this theorem is what's called proofer code. Proofer code. What is proofer code? Is a bijection between labeled trees that we have here and words, sequences of numbers, A1 up to n minus 2, an minus 2, where ai is just a number 1 up to n. So these are obviously counted by n to the n minus 2. There are n minus 2 times we get to choose any of the n numbers. So there are n to the n minus 2 such sequences. Each letter comes with n choices and there are n minus 2 of them. So proofer code gives us an elegant bijection. How does proofer code work? It's going to basically associate to this tree a sequence. And the idea is that I'm going to remove leaves. So remove the largest leaf and record, that's the code, the neighbor. So let's see how that goes in an example. And we'll do this example. So I'll think about who I'm going to remove. I'll keep a list of that and what I record. I'll keep a list of that. So let's do this as we go. So first of all, I look at my tree and I say, well, what is the largest leaf that I see? So my numbers are 1 up to 8. 8's not a leaf. 7 is, though. 7 is the largest leaf that I see. So I'm going to remove 7 from the graph. So 7 is gone. So let's take it there. I'm going to leave the edge there. I'll leave the node there just so we can remember it was there. What do I record? What was 7's neighbor? It was 6. So 6 is what I record. And now I look at the graph that's connected. Not this part, but I look at what's left. What is the largest leaf? Well, now my leaves are 1, 4, 2, and 3. The largest leaf is 4. So I'm going to remove the 4, and I'm going to record its neighbor. Its neighbor is 8. Remember, a leaf is a vertex of degree 1, so it has a unique neighbor. So this is a well-defined procedure. Okay, so now I've removed the 4. Now notice the 8 has become a leaf. So now when I look at my leaves, 1, 8, 2, and 3, 8 is the biggest leaf. Okay, so again, I'm going to record his neighbor, 5, and remove him from the tree. Okay, now my leaves are 1, 2, and 3. So 3 is the biggest leaf. 3's neighbor is 5. So we'll take that one off. Now what do I have? Well, 1 and 2 are my leaves. 1 is never going to get removed till the end, right? 1 will never be the smallest leaf. So 2 is going to be removed. We're going to record the 5. Okay, now we're down to this. 5 is my biggest leaf. 5's neighbor is 6. Now, 6 is my biggest leaf, but now I'm going to stop. Right when you get to 1, you're going to stop. Okay, why are you going to stop? Well, what we want to think about is now we've got this sequence right here, and this is our proofer code. We've recorded this data, 68556. Oh, sorry, 5556. So this is length 6, which is 8 minus 2, and this is the proofer code. To see that something's a bijection, we need to know that we have a well-defined algorithm that maps us from our domain to our range. So we've taken a labeled tree, and I've shown you how to get this sequence. Now what I have to do is take a sequence and show you how to construct a tree. So let me do that. So let's take the sequence that we had, and let's see if we can reconstruct the tree from our proofer code. So the code that we had before, and I'll do the same one so that we can see that it really works. 6, 8, 5, 5, 5, 6. There's my proofer code. All right. So what I'm going to do is I'm going to write down my leaves. So my leaves, if I think about this as coming from proofer code, my leaves are the numbers that don't appear. So 1, 2, 3, 4, not 5, not 6, 7. These are my leaves, okay? The numbers that don't appear. So these are all the numbers not in the proofer code. So how do I know there is such one? Well, this is length n minus 2. There are n possible numbers, so I'm going to get at least 2 leaves, which is great because that's how many leaves a tree will have at minimum, right? At least 2. So here are my leaves. Now what am I going to do? I'm going to pick the biggest leaf and reconstruct the tree. So biggest leaf and reconstruct the tree. So my biggest leaf is 7. That's what I'm going to start. So 7. That's my biggest leaf. So if I think about my proofer code, what does that mean? That means the first thing I pruned was the 7. So what I'm trying to do, if you'll remember, what I had before, right? I removed things and I recorded. What I need to do is reconstruct this top sequence. That's the first thing I'm going to do, and that's going to tell me how to reconstruct my tree. So I know that the 7 is what I removed. And the 7 is connected to the 6, because that's how it goes, like this. Okay, and now I'm going to look again and say, well, now what do I have? Now what's my biggest number that's a leaf that's not in here? Well, it's the 4. Who's the 4 connected to? So the 4 is going to be next. The 4 is connected to the 8. But now I have to look at what's left on my proofer code. So I've eliminated 4 and 7. So these are no longer leaves. But now I have a new leaf candidate that's been added because I've taken out the 6 and the 8, but there's already a 6 here. So 8 is not in this subsequence. So now 8 is a candidate to be a leaf as I continue with my proofer code. Okay, so 8's now a candidate to be a leaf, and 8 is in fact the biggest leaf that I see in my leaf candidates. So 8's done being a leaf. So 8 must be the next number that I wrote here. The 8 is connected to the 5. So the 8 is connected to the 5. Okay, and you can see I'm building up my tree here. It's not connected graph yet, but that's okay. It won't be connected until we're done, because remember, trees are minimally connected graphs. Okay, so now I've taken out that 5. I still have 5 and 6 not in my list, so that's fine. My biggest leaf that I see next is the 3. So that means that I'm going to record. So up here, what I removed was a 3. Who is 3 connected to? Well, I put it above a 5, so the 3 is connected to the 5. There we go. Biggest leaf I see is 2. I'm going to write that down up top. 2 is connected to 5. So let's put in an edge. 2 is connected to 5. But now, if I look at my suffix, right, now I'm here with constructing it. I have only the 6, so the 5 has now become a candidate for a leaf. So the 5 is my new leaf. The 5 is the biggest number I don't see, so the 5 is going to go up here. The 5 is going to be connected to the 6. And now, what do I have left? So I've got my 5. I've trimmed off here. Whatever's last, this guy, has to have been the thing that was connected to 1. Because of the way the proof or code worked, we never picked the 1 off. The 1 is the last thing there, so the 1 had to be connected to the 6. And you can see that I've reconstructed the same tree with which we began. So this gives us a bijection between labeled trees and words of length n minus 2 on the alphabet 1 up to n. And that tells us Cayley's theorem, which is that the number of labeled trees on n is n to the n minus 2.